I got you before lunch. Okay, good. All right. So I'm Drlica-Wagner. Just to give you a little introduction to myself. So I'm a scientist at Fermi Lab. That's the picture on the top left there. And an associate professor at University of Chicago. That's the picture on the right there. So I spend my time basically driving back and forth between these two places. That's most of my life, it seems like. Fermi Lab, you probably won't get a chance to visit this time you're out here, but it's about an hour out in the suburbs. It's the nation's premier particle physics laboratory. You may not associate Fermi Lab with astronomy, but actually Fermi Lab was one of the founding members of SDSS and has led a number of surveys since then. And now, as you're all probably familiar, Rubin Observatory sort of inherits from all of this involvement of the Department of Energy with cosmology and with building these large astronomical instruments. So my path to standing in front of you today started in graduate school working on a high energy gamma ray telescope. It's called the Fermi Large Area Telescope. I was not an astronomer by training. My PhD is in physics. My bachelor's is in physics. So I am, as much as you all, learning data processing. Right? Over the last few years, it's really been a crash course in learning how we do astronomical image processing for optical and near infrared data. So from Fermi, as a postdoc, I started working on the dark energy camera, which is on Cerro Tololo, Inter-American Observatory in Chile. It's the mountaintop adjacent to Rubin. So you can see the two telescopes from these adjacent mountaintops. And nowadays, I work a bit still on the dark energy camera, but a lot of my time on Rubin Observatory through commissioning and validation and verification. So Colin, who's back there, is my boss in Rubin. Okay. So why am I here standing in front of you talking? I just told you I'm a physicist. What could I possibly know about anything? That is a good question. So I think why they asked me to come give this talk is that over the last 7 years, one of the things I've been trying to learn a little bit more about is charge coupled device CCD detectors. So this is a picture of the lab out at Fermi Lab. Each of these stations here, so these little blue cubes, they look kind of cool, kind of sci-fi-y. Each of those houses a scientific CCD. We do a lot of CCD testing, a lot of CCD development, really working on pushing CCD technology to the next generation of detectors for astronomy and particle physics. And probably Brian or Adam or someone saw this picture of me actually touching a CCD, and they were like, "Oh, let's get this guy and give a lecture about detectors." But okay, and I do have some CCDs to show you. And so, okay, I'm supposed to like break this down, put you at ease so you can learn better. All right, so here's a fun fact about me. Sorry, this picture is kind of bad. That's me. I was a semi-professional ultimate frisbee player for a while. I am not anymore. I play with some dads at like 7 in the morning. My life is changed. But anyway, I have interests outside of what we're doing here today. Okay. All right, so let me get a show of hands. Who has taken a picture? Okay, I see some people didn't raise their hands, which is surprising to me, but okay. How many people have taken a picture with a camera that is not your cell phone? Okay. How many people have taken a picture with a camera that used film? Okay. How many people have developed that film yourself? Okay, good. You guys can teach me something. Good. I have done it, but not in a long, long time. How many people have looked at a raw image coming off of a CCD on a telescope? Okay, good. How many people have held a CCD in your hand? All right, cool. Well, so hopefully by the end of this week, we will get everyone's hands raised for both of those last two ones as well. So, so what we're really interested in is photon detectors. We're interested in collecting photons from astronomical objects. These photons have been traveling to us sometimes for billions of years. It's a real shame if they hit our detectors and we don't collect them, right? That whole lifetime wasted. So there are many ways that we can, many technologies we can use to collect photons. There are biological detectors. This is a microscope image of the retina of your eye, rods and cones, probably you learned about in high school biology. These are light-sensitive cells that use chemical reactions to collect photons. Photographic plates, these are chemical detectors. If you've taken a picture with film, developed that film, that's a chemical mechanism for collecting photons and developing it. And then our current technology that is in every camera that you have in your cell phone is solid-state detectors. They're actually not CCDs in your phone anymore. They're CMOS detectors. We could talk about that more. I'm not going to talk about it much. But these are solid-state detectors that use the photoelectric effect and the awesome properties of silicon to do our light collection and measurement. All right, so in order to collect that light, you need telescopes. This is kind of a telescope, maybe not exactly, but this is your eye. This is one of a great biological detector, like collecting device. So the idea is that you have an image, you have photons coming from something far away, it's into the cornea of your eye, gets focused on the back of your eye, the retina, where the photons illuminate those light-sensitive cells. That's what produces the image. And those cells produce some neurotransmitter signals that activate the optic nerve in the back, and then it goes to your brain. Your brain does all of this really cool image processing that makes you able to see the world around you. Here's another telescope, right? It's the same kind of idea. This is a camera. So again, the light is coming in, it's being focused. In an old-fashioned camera, you have some mirror here, which redirects the light so that you can see what you're looking at. And then you have a shutter, a mechanical shutter that flips up this mirror and basically exposes and pulls back a shutter and exposes the film or the light-sensitive detector device that you have at the back there. Again, intending to capture those photons and as a focused image. So film, which is not a solid-state detector, it's a chemical detector, works in essence. People who have developed their own film probably know way more about this than I do. So over lunch or sometime you can teach me even more about film development. So the basic idea is you have an emulsion of a silver halide, which is a chemical that's light sensitive. When photons hit it, it changes color. You can then develop that film, basically lock in the crystals that have been activated by the photons. That's the process of developing the film, and then you have an image where basically where light hit the film, it's dark. Where there was no light hitting the film, it's light. That's a negative image. And then you can do all kinds of post-processing things to that. Some of the issues are that these silver halide crystals, hopefully you can see it here, so they're not very uniform in their structure. So it's a little bit hard to do precise measurements of the positions of the photons in the silver halide crystal. They're also not all that photosensitive. So there are a lot of photons that will pass right through your film that won't activate the crystals. So you lose photons that have been traveling to you. In addition, the response of the crystals is not really linear. So how dark the crystals become or how dark your film becomes is sort of proportional to the number of photons that hit it, but is not directly proportional. And so going from how dark a part of your film is to how many photons hit your film is a difficult thing to do. Nonetheless, and color film works basically on the same principles, but you have multiple layers. Each layer is sensitive to a different wavelength of light. You illuminate all 3 layers, and then you develop the film, and you get the color image out of that. So even though film is not optimal, it's been used for astronomy for a long time, basically up until the 1990s, which for you may seem like a long time ago. For me, still doesn't seem like that long ago. But film had many properties that were much better than using your eye to try and do astronomy. So even before film was in place, there was astronomy. There were astronomical measurements. They were done by eye. There are papers where people are basically comparing how bright a star appears to how bright some standard source in the lab appears in order to do photometry on stars. But that was done all by eye. You don't capture anything. It's really hard to do precise measurement. It's really hard to do reproducible measurement. You have to do it all in real time. So this is Yerkes Observatory. This is a refractor telescope. It's 40 inches in diameter, about a 1 meter telescope. And it was used for a number of astronomical investigations. Generally with photographic plates were used as the medium. So I will show you some of those. Okay, so all right, so at Chicago, there's a project to digitize a bunch of these old plates from Yerkes. I'll pass this around. What this is, it's not an original plate. It's what's called a lantern slide. So it's on it, you can hold it up to the light. And you can see there are 3 different images on it. I'll show you the next slide. This is what it looks like. They're images of the Pleiades. On the top right here, this is sort of an in-focus image. It's sort of super saturated, so you can't actually tell how bright the bright stars are in it, right? The film has been oversaturated. You don't get any contrast there, but you're able to see the diffuse emissivity around the Pleiades. On the left is an out-of-focus image. You can hopefully start to see some contrast in the brightnesses and sizes of the dots, which are the bright stars in the Pleiades. And then on the bottom, it's the same measurement, but with a prism in front, where it's taking a spectrum of each of those stars. So I'll start passing this around here. It shouldn't be too fragile. I'll also pass around, so the students have been digitizing these images, have also been going through the process of taking plates themselves. So these are glass plates with an emulsion on them. I'll start this one here. So this is a spectrum of, I think that is just the solar spectrum, but what you should be able to see there, and is actually an emphasis of a lot of this lecture, is just how hard it would be to try and do precise measurement on something like that. And then I've got one more thing. So this is a solar spectrum that was taken on film rather than on a glass plate. Okay, so as you get to the end of the row, just pass everything back and take a look. So this is to give you a sense of where things were as recently as the 1980s, that people were doing astronomy with chemical detectors like this. Today, we've moved to much different designs for our telescopes. So this is the telescope mount for the Simone telescope at the Rubin Observatory. As you can see, it's much squatter than that refracting telescope that was being used back at the turn of the 1900s. This is actually a unique optical design, or a novel optical design. It's a 3-mirror design. The light actually comes in, illuminates the primary mirror, which is divided into 2 sections. It illuminates the outer annulus of the primary mirror, bounces up to a secondary mirror, which is up here, held above the telescope, and then back down onto another part of the primary, which is called M3, which then directs the light into the camera there. And what we're going to be talking about is the camera itself. And so these are 2 different wide field cameras. On the left is the dark energy camera. That's an assembly of 70 CCDs, 62 science CCDs. They're 4,000 pixels by 2,000 pixels, so 8 million pixels per CCD, arranged into an array like that. And on the right is LSST cam. It's 189 CCDs, And these are each 4K by 4K, so 16 million pixel CCDs. So I'm going to go to the back, and I'll start these going from the back. So these are two CCDs. This one is a DCAM CCD. It's a 2K by 4K CCD. This is a DESI CCD. It's a 4K by 4K CCD. So this is fairly similar to the LSST CCDs. One difference is that the pixel size is a bit larger here. So pass these then forward, okay? Be sure to look at the back of those CCDs. That's where the fun part is. Okay, and then I have one more at the end if you want to see what it actually looks like when you're working with one of these. I have one of these in like the mechanical package, so you can come up afterwards and get look at this. That one is not protected by plexiglass. Yeah. All right. So what are the desirable properties of your photon detectors? So your photons have been traveling for say 10 billion years. You don't want to lose them, right? They made it all the way to you. They happen to hit this very small piece of glass that was your mirror and be focused into your camera. Once they get there, you really don't want to lose those photons. You'd like to, as much as possible, determine exactly where on your detector each photon hit. Right, that is how we measure or associate photons with astronomical objects. You'd like your detector to cover as large an area as possible, right? You would like to see as much of the sky as you can at a single time, and if possible, with no gaps. Of course, that's not fully possible. We can talk in great detail about the maximum size of CCDs that we have. We have CCDs that are bigger than those that I'm sending around, but there are issues. Ideally, you'd be able to determine the energy of each photon that hits the detector. These CCDs, generally speaking, silicon in optical and near-infrared wavelengths is not energy resolvent, right? So we can't tell the wavelength of a photon when it hits our CCD. That's why we put filters in front of our cameras. There are energy resolving detectors. We're not going to talk about them. They're generally, when you get energy resolution, you generally lose one of the top three things in return for it. But this is what detector development is. This is technology development. You know, 50 years from now, CCDs may look like the film, or may look to us like film does now, right? And every detector that's in a camera may be energy resolving. It's possible. We'd like to tag the timing of each photon. You know, if you're observing very fast transients, you might want to know exactly when each photon arrived. Generally, for the scale of objects that we're interested in optical and near-infrared astronomy, we're not that interested in time tagging at like millisecond precision. But for a CCD image where your exposure time is 30 seconds, you don't, or 60 seconds or 90 seconds or 5 minutes, you don't get any internal timing resolution within that exposure. You only see the photons after you read it out. You don't get to measure exactly when they arrived. You might want to measure the polarization of each photon. I'm not getting into that. There are detectors of polarized photons that we're not going to talk about this. And then finally, you would like to do all of these things as cleanly as possible without introducing more noise into your measurements. So ideally, you would measure just the photons that arrived, and in a super ideal case, just the photons from the astronomical object that you're looking at. But generally, that is not, we're not in the ideal case, and there are various sources of noise and various artifacts that leak into your images. Okay. All right, so we're going to talk about CCDs. The 2009 Nobel Prize was awarded in physics to the inventors of the CCD. This is Boyle and Smith. They were at Bell Labs, and they're actually sort of part of this project that was being developed to do FaceTime, in essence, right? They were trying to develop FaceTime back in the 70s. Of course, they were pretty far away from actually having FaceTime, but the development of technologies that are able to both collect light digitally and reliably and quickly and digitize it, and then even project that light as a video signal. All of those were technologies that AT&T was developing at the time. So this is them sort of posing for a picture with their CCD camera that's showing a picture of the face. All right, so how do CCDs work? So at the foundation of the CCD is the photoelectric effect. So a photon comes in, it interacts with an atom of silicon. It takes an electron and energizes it from the valence band to the conduction band. So it basically frees an electron. Silicon is a lattice, so at the same time that it frees an electron, it also produces a positively charged hole. This is, not it. How you think about holes and electrons depends, but both of these are charge carriers. You could think of the electron as moving from atom to atom drifting through the lattice. You can also think of the hole as moving through the lattice, basically as silicon atoms trade electrons to replace the hole. So basically your hole can move as well as your electron, right? It's always the electrons that are doing the motion. It's just whether it's a positive charge or a negative charge in that that's moving through here. And there are CCDs that collect both of these. There are electron collecting CCDs and there are hole collecting CCDs. Both of these exist. Both of them are used in astronomical imaging. So the way you move these charges is by applying an electric field of a voltage potential, and the charges will drift in opposite directions in that potential. So right here, I have a monolithic sensor. I have no pixelization. And so basically, by applying a voltage in this direction, I cause the charges to move vertically, but I haven't confined them laterally, right? And that's not super useful for me if I'm trying to get an imaging detector, because I want to know where, not just that my photon hit this chunk of silicon, but where on the chunk of silicon I hit it. So what I need to do is I need to create pixels, and that's what was done with the first CCD. So I love this drawing because it is the one, it like looks like a centipede or a millipede, which is fun. But also I think you can with a little guidance understand everything that's going on here. So so let's try and do that. Okay, so the first thing to look at is we've got some wires. These are just wires, right? Like this is copper. It's got some insulator on it, and it's attaching to this metallization structure on the pad here. So you've got wires. You've got relatively few wires. That's another thing to note. That's important for CCDs. The number of wires that you need to control a CCD are relatively small. You have some surface, some substrate. This is silicon. So underneath all of this is silicon substrate, and resting on top of it is a metal oxide, so a metallization layer that is essentially just like little wires that are built into the surface of the CCD. Okay, so I'm able to, by putting a voltage through this wire, I'm able to change the voltage on everything connected to this line, right? Okay, so that drives the voltage of all of these parts of the CCD. If I look at this line, it passes a voltage, it actually goes underneath here, right? It passes a voltage to all of these parts of the metallization, and this wire controls all of these parts. Okay, so I've controlled independently each of these three parts of the CCD with three different wires. And that's critical. So these two wires are passing some signal into the CCD. They're depositing some charge onto the CCD. The original CCD wasn't developed necessarily as an imaging detector. It was developed as a way to store information. It was a memory device. So basically you put some electrons in here, and then the goal is to pass them through the CCD and to read them out on the other side. Okay. So you put them in here, and then you can control the voltages in 1, 2, 3, these 1, 2, 3 sections of the CCD independently with these 3 wires. And that's what actually forms the pixel. Right, so these 3 sets of wires here, these metallization layers, by controlling them, you're able to confine the charge in a specific region of the CCD. So all of the confinement is being done with electrical potentials. So basically you set up an electrical potential barrier that makes it impossible for charge to flow past, say, this wire, right? So any charge on this side can't flow this way. And then this wire here is controlled at the same voltage as this one here. So now any charge between here and there is also confined to here. Okay? And you confine the charge in each pixel. So confinement is great, right? It keeps the charge from spreading out across the entire device, but it doesn't allow you to measure the charge confined in each region. The other critical part is you need to be able to move the charge through the CCD. Okay, so confinement is great. Confinement keeps the charge where it was generated, but you need some motion to generate a readout to be able to measure a charge. To be able to move the charge from one side to the other side so that you can measure it at some output gate here. So how does motion work? All right, so in a pixel, I said we have 3 wires, 1, 2, 3. They can each have a different potential set on them. So if I start in a configuration where this wire is at a low potential, basically I have a well here where I can collect electrons. And these 2 wires are at a high potential. I have a wall that keeps those electrons from flowing into my next pixel. In this next pixel, it's the same configuration. So the first one is low, the other 2 are high. So again, I have another well here that's confining my electric charge to the pixel. So this is at time 1, T1. At some later, so this is 1 pixel here, and this is the second pixel over there, right? At some later time, just by changing the voltage coming into, in this case, wire 2. So wire 2 is down here. So I change the voltage coming into this wire. I drop it. So now my well is longer. So the electrons can flow and fill this entire region. So in between these 2 wires, right now the electrons can be distributed here. And then later what I can do is I can raise the voltage on clock 1. So now I've moved the charge over a little bit. And then I lower clock 3 and the charge is able to move to the right. And if I then go back to the configuration I was at before, I've moved the charge basically from here to here, and then I can repeat and I can get it back into here, and I can just shuffle the charge through by doing the sequence of shifts and voltages. So that was the first CCD. This is a more modern CCD. This is a microscope image of the corner, what you would see if you looked at basically the corner of one of these CCDs. Yeah, if you're done with it. So each of these is one of these little wires, just like the wires that we saw in the original CCD. Our technology for doing photolithography on silicon has come a long way since the 1970s. So these wires can now be very, very thin. The spacing in between sort of these sets of 3 wires can be of order 10 microns, a tenth of the human hair. 10 to 15 microns are common pixel scales. But the concept is exactly the same. That by controlling just the voltages on just 3 wires, I can confine the charge to specific regions of my silicon, and I can move the charge through the silicon without ever letting charge leak from one pixel to the next. Yeah.
Can you find some way to create wells in the pixel?
So there can be tunneling. Generally, it is it's so suppressed that it's not the actual charge. It's not the systematic that we worry about most. More we worry about actually not. So when the charge, when the charge moves from here to here, and then you raise the next potential, sometimes you don't actually drain all the charge here. A little bit of charge gets trapped and left behind. And that's the more common way that you have charge leaking between pixels. Quantum mechanical tunneling is of course possible, but for this, for the distances and the size of the potential barriers, it essentially doesn't happen. Yeah, in the back.
Are those three little shaded regions like the same potential walls that you're showing?
These three are these three wires. So they're the three metallization layers on the top of the CCD. So they're carrying an electrical potential, and the wiring is like it jumps over here, and then so these two get controlled off of the same wire, so they have the same potential. Yeah.
Is there a particular reason why 3 is the optimal, or is it isolated, or just historical?
So there are CCDs that are built with 3, 2, or 4 of these controls generally. I've only ever worked with ones that have 3, but they get used. 2 or get used as well.
I think I had missed the previous step here. Why do we need to bring the electrons across the pixel to read them?
Great.
Why
Okay.
can't we just read it from the first band?
Why can't we just read it where it is collected?
Yes.
Right? Okay. So in the 1970s, this just wasn't possible. You couldn't build a readout structure for every pixel. Nowadays, the phone in your camera, which is called a CMOS detector, actually does do this. It reads it out at each pixel. But what that means is that each pixel then has its own electronic response. So each pixel has its own readout structure, its own amplifier, its own signal chain, which means you need to calibrate each pixel individually. And this has been one of the major hurdles for adopting CMOS in astronomical imaging. In astronomical imaging, I only need to calibrate the one amplifier at the end of the chain. And that amplifier sees the charge in every pixel. Okay. So it's a great question. This is the way we're moving. I mean, LSSTs did pretty significant studies on CMOS detectors at the early days, and they chose to go with CCDs. The next project hopefully would choose CMOS. I don't know. Hopefully CMOS is far enough along. Yeah.
So I'm just
Yeah.
curious
Silicon. Okay. So there are a few things about silicon. So you can make CCDs out of other materials. People have made CCDs out of germanium. Generally, you want a semiconductor, right? You need a semiconductor, and you want something with a band gap energy that is in the wavelength range of the photons that you want to collect. And so it turns out that the silicon band gap basically goes from 1100 microns, 1100 nanometers, so 1.1 microns, up through the visible, and then in the UV and X-ray, you start being able to produce multiple photons, multiple electrons per photon. But in essence, silicon is well matched to the wavelength of light that we want to observe. It also is relatively common, and it's the most prevalent semiconductor that we have in the industry. So all of the stuff that I'm talking about here uses a lot of the same technology that's used for microchip fabrication. It's very similar types of processes.
I have a somewhat similar question to that. I mean, there's like people who research like alternative semiconductors, like graphene and germanium, stuff like this. They're doing research into
So I haven't heard of graphene as one. So germanium is the one that people have been, that I know people have looked at most seriously. At other wavelengths, like in the infrared, you use a different technology. So like mercury cadmium telluride is the technology that's often is used for the infrared detectors. I don't know, Colin, if you know, are there other detectors? Indium gallium arsenide, yeah.
This might be a dumb question, but does it ever get a problem of the speed that you're transferring the electron? Does it ever get a problem that like, oh, maybe I'm just throwing in electrons faster than I'm actually.
Yeah, okay. Yeah, so it's a great question for sure. So the general way that we operate these CCDs in most, I don't want to be too expansive, but most ground-based imaging capabilities is that capacities is we open a shutter, we collect the photons, we close the shutter, then we transfer the photons. So we're generally not collecting photons at the same time we're transferring them, because if we were, we have some ambiguity about whether that charge packet was created, at what location that charge packet was created. So we generally do this two-stage operations where we expose, all the charge is confined, we close the shutter, and then we shift it. Does that make sense? But that's not always, I mean, there are cases where you want to read out and expose at the same time. That definitely does happen. I think CTF did this for a while for really fast transients. And you can do that. Rubin was doing this to, well, okay, now I'm digressing, but yeah, you can expose it at the same time. All right, so what does this transfer look like? So good, this is a good transition. This is exactly what I was talking about before. So generally, you open your shutter. This is the characteristic bucket brigade analogy that's used for CCDs. You may have seen it before. You open your shutter, the photons rain down into your pixels. While this is happening, none of the charge is moving. You're confined, your clocks are fixed, your voltages are fixed, you're just confining the charge into pixels. You close your shutter, you stop the rain of photons, and then you start shifting the charge. So the problem you have is you have a 2D array of charge, but you only have one readout structure. So that means you need to shift the charge in two directions. So generally what's done first is we shift all the charge in what's called a parallel direction. So every pixel moves in one direction, and the last pixel in the column gets dumped into a special register, which can also move the charge in the second direction. So you move all of the charge one row over, and then you read out that row. You move all the charge one row over, you read out that row. And so this is the way we do a sequential read of a 2D array of charge in pixels. So it looks like the movie that's going like this. As you should be asking yourself, and the question about why not just read out at the charge at the pixels, the main thing you sacrifice by doing it this way is speed. This is not a fast way to read out a detector, right? What you gain is that everything gets read out through the same measurement device. And so the calibration, if you can calibrate that device, then you do better. Okay, and so this is just another picture of that, right? So if you want to read faster, you can take intermediate approaches. So instead of reading, instead of going all the way to reading each pixel with its own amplifier, you can instead read an image with, say, 4 amplifiers or 16 amplifiers. And so this is an intermediate step. So it allows you to break the image into smaller chunks and thereby read it faster without going all the way to having to calibrate the same every pixel independently. And for the CCDs in LSST-CAM on Rubin, they actually do this with 16 separate amplifiers. And so this is what a raw image looks like. This afternoon, you're going to load this and play around with it. But you can see there are 8 chunks on the top and 8 chunks on the bottom. Each of those is read out by a different amplifier. each amplifier has a slightly different performance, which is why the background level of each amplifier is slightly different, right? That's not physical. We're looking at one region of the sky. The brightness of the sky doesn't change very much from over here to over here, but the two amplifiers have different performance characteristics, and so they appear different. Yeah.
Is the pattern, like the gradient we're seeing in the colors, intentional, or it looks like we have the darkest one at the top? I guess.
That's a great question. I don't know whether the biases were intentionally set this way. Colin, do you know? Yeah, I think it just happens to be the case. It's a good question though, because they're definitely, we'll maybe talk about this a little bit, but adjacent amplifiers do talk to each other a little bit as well, and so it isn't like this amplifier knows what's going on in this amplifier better than it knows what's going on in this amplifier. Right? Like it's inductive crosstalk between the wiring. So like the physical wiring of those two amplifiers is actually closer. Okay. And just to emphasize it, more amplifiers, more problems. The same thing that I said was an issue for CMOS is an issue for as you go to more and more readout amplifiers, but going to 16 versus 16 million are pretty different problems. Yeah.
I'm not sure if I have a fully formed question yet, but like, how do you calibrate all the amplifiers to work together? Like, especially in a CMOS system where you can't, for example, line up your target and a standard on one amplifier.
Yeah. So I think maybe Colin will talk a little bit about calibration products more, but in essence, you try and do exactly what you were saying, right? It's difficult to put a star on every CCD, but you can expose your CCD to a flat field frame where you expect the same amount of light to be hitting each of the pixels, right? And variations in the pixel performance can be measured by increasing the amount of that light, right? So you start off with a low light level on every pixel and you increase to higher light levels. This is called a photon transfer curve. And so there are various different calibration products that you can take to try and cross-calibrate the performance of different amplifiers or different readout structures. So another thing you might notice from one of these amplifiers, so not only is this broken into 8 chunks on the bottom here, in just one of these chunks, you see a brighter region and darker regions. This is because in the readout structure, one of the calibration products we would like to take is just to understand what is the response of my amplifier, of my readout structure, when it's measuring nothing, right? When there are no photons actually being collected. So what we do is we generally, in our bucket brigade, we read a little bit longer than we would need to. So what we actually read is we read past the end of the CCD. So these are pixels that are not physical. They were never collecting photons. They're just artificially created by shifting the charge, continuing to shift the charge beyond the edge of the actual pixel region. These are called overscans. The types of pixels are called virtual pixels. In essence, you're just continuing your charge transfer, but now there's no charge there to actually be transferred. So all you should get are empty readings. And this is important for measuring the 0 point or the bias level of your amplifier. So when your amplifier is reading nothing, this is what it reads. Yeah.
Does that affect being contiguous, which you said was a desire for these things?
So because this is these are not physical pixels, this is not an actual physical gap. So it's created electronically. So your CCD is completely contiguous, but when you read out a section of the CCD, you decide that you'll read several additional columns, which actually never collected. They're not real columns. They're just continuing to read. We should talk about this more. It can be a challenging concept. Yeah. Any question or?
Oh,
Yeah.
so like, if it's like 16 wide on your CCD, but if you were to look on it, like when you got it, it'd be like 20 instead, because you have like extra rows, whatever.
Right, so yeah, so if this, if the physical dimension of the CCD is 4,000 pixels, when you read out these extra pixels, the size of the image that you would get would be bigger than 4,000 pixels. You haven't expanded the physical size of your CCD or anything like that. You're just adding extra pixels onto the end, and that's why it appears discontinuous. This is like one of the main things when you look at raw images, you're like, what is going on here? Right? Okay. So how am I doing on time? All right. What are some things about the detector that you care about? So one is your efficiency for collecting light. So here are some silicon wafers that have been grown and then cut. They look like mirrors. Generally, you don't want your photon detector to look like a mirror because that means the photons are bouncing off of it, not going into it. So what's commonly done to these detectors is that a layer of what's called anti-reflective coating is put on it. Silicon itself is very reflective, but you can coat your silicon with a material that has a refractive index that's in between silicon and vacuum or silicon and air. And when you do that, you greatly improve the efficiency of light getting into the silicon. So generally, you're sort of painting on this anti-reflective coating. The same thing is done to glass on windows where you don't want to see your reflection. And that's why LSST camera looks like this. So you can see different CCDs look different. That's because they have different anti-reflective coatings on them. There are actually two different manufacturers for the CCDs in LSST cam, and they use different processes for doing the AR coating. They were trying to be matched up as well as they could, but the processes are different and it's apparent. And so one CCD manufacturer delivered the CCDs that are in the inner region, the other manufacturer delivered the CCDs that are in the outer region. So another thing that's important is the absorption depth. So lower energy photons travel farther through silicon. Eventually you get photons that are such low wavelength that they get all the way through the silicon and you just can't collect them. They're at lower energy than the silicon band gap. So they can't promote electrons, they just go straight through the silicon. If you want to be sensitive to near infrared photons at 1 micron, you need really thick detectors because they have a very low efficiency for converting into photoelectrons. On the other hand, for very short wavelength photons, they convert almost instantaneously at the surface of the CCD. So you want your CCD, ideally your CCD to be sensitive to both of these, to both the photons being converted right on the surface and the ones that pass through almost all the way through the CCD. Here are curves just of the absorption length. Don't worry about it, the concept was on the last slide. The desire to collect these infrared photons has led to really a revolution in the thickness of these CCDs. So these are skyscrapers. On the right are single pixels, the aspect ratios of single pixels from some recent cameras. So in all cases, so if this were 15 microns in pixel size, then the height of the pixel, which is 250 microns, would lead to an aspect ratio that looks crazy even by skyscraper standards, right? So when we are thinking about the confinement of electrons to pixels, you're talking about generating an electron down here and having it stay in the pixel as it drifts all the way to the top there, right? So it's like running up a skyscraper. That's how confined you have to be. But all of this goes into increasing the quantum efficiency, which is now quite good for modern scientific CCDs, and can run all the way from, say, 250, 300 nanometers, so the UV edge of the visible, all the way to 1.1 microns. And the way you do this is by having good charge collection efficiency, very thin coatings on the surface of the CCD, so that the blue photons can still be collected, and very thick CCDs so that the red photons can be collected. And sometimes, depending on whether you're optimized for one wavelength range or another, you'll have separate CCDs for these two applications. Of course, nothing's perfect. And you can see variations in the quantum efficiency. These generally are most apparent in the blue wavelengths, which are converting right at the surface. On the surface, you've done this extra painting or annealing, some process to try and apply your AR coating, and that is non-uniform. Just that process ends up being non-uniform. The two different CCDs, which we saw in the LSST focal plane, having different colors. If you look at their quantum efficiency in the blue, in the U band, the UV filter, you see that the patterning is very different. This one used an annealing, microwave annealing. This one used a chemical process. We call these coffee stains. Okay, so we're trying to localize charge. Of course, we're trying to localize the charge within this very narrow aspect ratio skyscraper. As it drifts very long distances, it can diffuse. How much it diffuses depends on how large of a voltage you've set up to confine it, right? So there is an optimization problem to be done there. But you can see this diffusion happen. There are cosmic ray tracks that go through the CCDs. You can tell that this is when it was close to the bottom of the CCD, and this is when it was close to the top of the CCD. Well, the readout side of the CCD, bottom and top, we should talk about, because it's wider here. So the charge had to drift a farther distance to get to the readout structure. The charge itself has an influence on the electric fields that are creating these pixels. So here I just converted a photon into an electron somewhere in the CCD there. That electron follows the electric field lines to run into a pixel. But if I put 50,000 electrons in one of those pixels, that changes the electric field line structure. And so if I were to create that same electron here, when there are 50,000 electrons already in this pixel, it would go to an adjacent pixel. It would actually change which pixel the electron ends up in. And this is called the brighter, fatter effect. It turns out that as you deposit more charge into a pixel, the effective size of that pixel shrinks, right? It's harder to put more charge in there once you already have charge. And this is measurable and happens in all, essentially all of the scientific CCDs that are operating today. You can also see all kinds of weird things from the fact that the CCD is a mechanical package, right? So the DCAM CCDs, the way that the CCD was attached to the package was with double-sided sticky tape at the corners, right? And you see that distorts the structure of the pixels. In LSST-CAM, there are mechanical structures that are holding things, basically are used to attach the CCDs to the focal plane. You can see distortions arising from those as well. Okay, I'm almost out of time. All right, the way we do charge measurement, I'm not going to get deep into this. This is a lot of electrical engineering. But in essence, you move the pixels onto an output stage. It's almost like you're putting them on a tiny capacitor, right? So you put some charge on a tiny capacitor, and that establishes a voltage across that capacitor, and you can measure that voltage. That voltage is very small, so the best way to measure it is relative to some reference. So you measure the voltage on the capacitor before you put the charge on it, and then after you put the charge on it, and you take a difference of those two measurements. And that is the measurement of the charge in the pixel, is that difference. That's an analog measurement that you make. You convert that analog measurement into a digital value using a converter. And that gives you the actual integer values that come out in your raw image, that ADC. Those are integer values of that voltage change. Generally, a small bias is added so that the ADC measurements never go negative. And you need to find that bias level and remove it in the raw images. The output has an arbitrary unit assigned to it, arbitrary analog to digital units or data numbers or counts. These are whatever has gone into changing that voltage change into a digital signal. It is proportional to the number of electrons that were in the pixel, but in order to get out the number of electrons that were actually in the pixel, you need to apply a constant of proportionality. That constant of proportionality is called the gain. It converts the electronic readout that you're getting from the detector into the number of electrons that were in the pixel. And that generally needs to be calibrated from the data, but for CCDs, they are extraordinarily linear, which means that single gain value ends up working for converting one electron, or for measuring one electron, or for measuring 100 electrons, or 1,000 electrons, or 10,000 electrons, which was not true for your photographic plates, right? They were nonlinear. So this is a demonstration of that linearity. So you can fit the slope of this, of the line. So as you put more charge or more photons onto the detector, you get more electric signal out of it, digitized signal out of it, and you can fit that constant of proportionality. And this is another talk, but novel detectors are also able to count individual photons. And so we can directly check that gain measurement from measuring individual photons, and the results agree to within 1%. So, all right. So there are a whole bunch of additional noise sources. We're going to look into those this afternoon on some real data. And I think that's where I'll leave you. Okay, thanks.
Just had a question about gain calibration. Now that your CCD is voltage, right? That also increases the temperature of the sensor. Does that also, is that something that you calibrate for when you're doing the gain factor calibration?
Yeah. So the amplifier is generally temperature dependent, and the voltage that the voltage from the electrons in the pixel going onto the capacitor is generally not what heats it up as much as the fact that you're shuffling all of these voltages to shift the electrons onto the amplifier and then shift it off. But the amplifier does heat up and its response changes. So often what people will do is even when they're exposing the CCD, they will clock the amplifier. Even though they're not shifting the charge onto it, they'll clock the amplifier so it's in a steady state, so that then when they start shifting the charge off of the CCD, the amplifier is already heated up. It's already at its steady state temperature, because otherwise you do see that response that happens when you start clocking the first rate of charge. But this whole thing is, okay, so we're going to do this this afternoon, is look at the biases, and you see a lot of structure even in pixels that are not real. They're just measuring the amplifier response. And all of this is, these things that are transient, temperature-related effects or electrical effects. Yeah.
Is it obvious how color comes into this, the filters and everything?
How color comes into this? Obvious. I'm not sure anything's. Okay, so the main thing, Colin can correct me or can add to this if he wants, but I would say that the main effect when you put a filter in front of a CCD, this is that you change where in the CCD the photons are converting. So if you put a blue filter in front that is allowing only blue light in, then all of those photons are going to convert near to the surface of the CCD. So you'll be most sensitive to effects near the surface of the CCD. if you put a filter for red light in front, all the photons that get through are going to be converting deep in the CCD. Some will even bounce off the back of the CCD and convert coming upwards. And so the main effect is you start seeing features that are related either more to the front side or more to the back side of the CCD.
When, just to follow up, sorry,
Yeah.
your hands up. CCDs were used for photography at one point, right?
Yeah.
How do they get 3 colors like RGB on a CCD
Right.
detector? So just having one filter covering the whole thing.
This is this is a slightly different talk, but what you can do is you can take sets of 4 pixels and you can actually lay down micro filters on top of them. So you can put different built-in filters on sets of 4 pixels. They put like 2 green and a red and a blue filter. And then, so those 4 pixels then become 1 pixel, right, of your image. But you lose spatial resolution by doing that. So for astronomy, we like having the flexibility of being able to change, put in different filters. We also like the fact that we have the full resolution of the detector by putting filters in front. I hope that made sense. If there were a chalkboard, and yeah.
It's sort of related to Nasser's first question. So it seemed like the quantum efficiency was, again, least good at blue wavelengths and better at red, but as you're saying, red photons are going to have to travel further up. So I feel like that would make it to photons being detected easier. Maybe there's a different effect.
So if you at the surface of the CCD, we had to put things like the anti-reflective coating, and there's another layer that's called the dopant layer, but we have to put some layers on top of the front of the CCD in order to make it work that are not photosensitive. So very blue photons will actually convert before they make it into the active region of the CCD, and that's why the quantum efficiency dies off at the blue. So they're converting on the surface of the CCD before we're actually able to collect them.
But the broad peak was still quite red.
So the broad peak,
Of
is
quantum
saying,
efficiency.
oops.
There are a lot of those detectors, at least. Maybe not all of them.
So you're saying like down here? Why is it here and not
650
here? Or 650
or 600-ish.
here instead of over
Yeah.
here? Okay.
Maybe another
So-
way to ask it is, what do you mean by quite blue?
Quite blue. So the feature that I was talking about is taking over around here, right?
Okay.
So that's why you have this fold up.
Yeah.
Variations from here to there are generally caused by what your AR coding is, how efficiently you can actually get the photons into the CCD and they don't reflect off. Because silicon is quite reflective and you generally are not 100% efficient for capturing those blue photons or you know, the AR coding matching to get them into the CCD. Does that make sense?
Thank you.
If you should, go ahead and get started with the lunch break. If you have any more questions, maybe put them in the Slack or email out, maybe address them when we come back for lunch. So Mike is happy to go with people, and everybody, people are already signed up, back in the room. Obviously, feel free to let's come back at 1:35. And yes, this is important. So the museum is open to the public. This door locks when we leave.